Cool. Right, excited everyone to get this October Hamilton Meetup off. So super excited to have Sholto present. Afterwards, we're going to just go over a few of the new features that we kind of added into Hamilton. So pretty excited for that. And so, in which case, Sholto, if you should be able to share screen, and in which case you can introduce yourself. But like for those who don't know, Sholto is a machine learning engineer at Capitec Bank in South Africa. He actually, correct me if I'm wrong, Sholto, but you actually presented this at PyData or PyCon South Africa.
Yeah, PyCon.
Yep. Yeah, so I think Sholto, I think you're probably as far as I know, publicly the first external speaker who's other than Elijah, myself, and Thierry, who've spoken on Hamilton. So super excited to see the development here. And if you want to share your screen.
Yeah, I'll share screen quick. Yeah, thanks for the intro. Yeah, let me quickly get this going. Yeah, when I present, I can't see anyone, so just please
we can help moderate.
Any questions or anything. Yeah. Cool. So yeah, today I just want to go through our decisioning engine that we built on top of Hamilton. Just as a quick intro, I'm Sholto. I'm a machine learning engineer. I did my master's in 3D scene understanding, and I have a passion for open source projects. I currently work at Capitec on the data science platform. And just for a brief introduction, Capitec is the biggest bank in SA on population. We have 22.2 million active clients, and that's 1 in 3 South Africans bank with Capitec. So with all these clients, we actually pride ourselves in being a data company. And with that, we process 60 billion records a day. We have 100,000 batch processing jobs that run monthly. We do 8 daily feature-related deployments and 7 million ETL-related queries. We also moved everything over to AWS, so we have access to some cool tools like Redshift and Amazon SageMaker. And then, yeah, Capitec is also driving a lot of open source projects. So, yeah. Today, I just want to kind of describe our specific use case, try and introduce some of the requirements we had and how Hamilton helped us solve these requirements. And then I want to dive into the decisioning engine that we developed and have open source now. And then I just want to do a live demo on everything. So just for some background on our problem, Capitec, a lot of people might think of data science just as like the machine learning or the model development side of things. But there's a lot more to it. You have to think of how you're going to get this model into production. So for us, for example, if you're trying to develop a fraud model, you have to think how you're going to get that fraud model in a space where you can actually invoke it with real-life transactions and get results from it. You also have to think how you're going to orchestrate it with potentially fetching other features, or maybe you have other models that you need to orchestrate before you can get the final result. And then a lot of these models give out scores between 0 and 1. So you oftentimes need some business logic after that score to give an action back. So there's some post-processing that you often need for it. And then with that post-processing, it's often good to try and incorporate some domain expertise. So again, for fraud models, you'll find oftentimes that as soon as you deploy them, their accuracies drop because people realize what you're looking for and adapt their modes. So it's oftentimes good to have some sort of quick rule-based model that you can incorporate new knowledge as fast as possible to try and counteract these new modes of fraud. And then finally, we really need these things to be explainable so that we can fully understand how they work end to end. So this led us to our requirements, or what we considered our golden standard. So firstly, a lot of these models, for instance, credit granting models, you might want to be able to score or calculate credit scores for all the clients on a monthly basis. But as soon as someone walks into the branch, you want to right there use the most up-to-date information to calculate their score in real time. So we want to be able to use the same code base to score client for both batch and real time to reduce the overhead. We also want to be able to allow it to be discoverable and self-documenting. So there's like certain parts of these components that might overlap between departments. Again, going to credit granting, there might be policies that could exclude certain populations based on certain features, and those policies might be common between retail credit and business credit. So we need them to be like discoverable so people can make use of them and reuse them between departments. We also want to make it like really quick for our data scientists to get these models out into production. So we want it like very easy to use and very quick to get out. And then like a lot of these things can all have these very large DAGs that they produce. So like we really need a way to focus on explainability and auditability so that you can drill down into it and understand what impact changing a particular node has. And then finally, that feeds into, we want each module to be modular. So like we want to be able to update a function and determine downstream effects easily. And that kind of leads into stateless execution, because if you update a particular function and you want to run multiple tests to see how it impacts performance, you don't want to like state to make things tricky to actually test. So that's where we found Hamilton with like these requirements, and we saw that it solved a lot of these issues for us, because like the DAGs that it produces are like very self-documenting, and it's very easy to paint that bigger picture on how everything interoperates with each other. It also enables that modular execution, because you can override values or only select subsets of the DAG when you execute. And then with the UI, you can kind of log your executions and produce like auditable workflows. And then finally, it's Python-based. So like our data scientists can use all the tools that they're comfortable with already to put these out into production. So I'm just going to do like a brief overview of Hamilton. I'm sure everyone's aware of it. But from that function, you can produce these DAGs. So each function on the left there produces a node on the right, and based on the variable in those functions, it's able to determine the dependencies between each of the functions. And then going to the execution side of it, this is where I was talking about that modularity, that you can put in the input values and say which output values you want. Or you can use that override to like run experiments and say, well, what if the output value of this was that amount rather than the amount that you predicted, and see the downstream impacts of that. And then you can obviously log these executions now to the UI, which is very useful for actually drilling in and seeing what executed, and then like going through the historic values and seeing what's changed potentially. So then on top of that, we decided we needed to incorporate like a lot of our own modules. So I'm going to run this through an example of a credit granting flow. I think I stopped these 2 slides, sorry. So we wanted to extend Hamilton to enable us to like build a common set of components that our data scientists like often use. So like by building that, it will obviously increase the ease of use of the platform, because they'll have a lot of familiar components that they work with a lot. And then on top of that, we have ways to abstract a lot of these components into config, so that people who are less technical can like maintain them on a day-to-day basis, or configure or change different thresholds depending on their needs. And then we already have like a whole ecosystem for deployment, so we wanted to wrap it in a way that it can fit into that ecosystem. So I'll take you through it based on this credit granting flow, which basically starts with a set of policies, which are basically excludes subsets of populations on actually getting credit flows. And then from there, you typically want to score these clients, calculate their credit scores, And you do that by first bucketing the population based on certain features, which is generally just like a decision tree, which assigns a label to each client. And then from there, we're able to determine which scorecard to run them through to produce their like credit score. And then finally, we bring it back to what price we want to give that particular loan to the client at. And for that, we generally use a pricing table. So the library that we made, we first have this, one of the components is that decision tree that you can build. And we use the decorate approach where you first define the tree at the top, and then you have certain conditions that that tree can fit into. So here's the root of the tree, and then underneath it you have the various conditions, which are these two parents. And then under that you can have various child conditions. And then the outputs can either be values that are produced earlier on in the Hamilton execution graph. I'll show a bit more on that later. And then, or they can be like static values that are inserted in the tree. And then having them as functions is very powerful because you can use like arbitrarily complex predicates, or you can even put an entire model into this function as part of the decision tree. So this visualization is just a visualization of the tree, but when you bring this into Hamilton, it becomes this execution graph that you can visualize. So the condition here, which you saw before, that child one, actually becomes this node in that Hamilton graph. And then the tree at the top, we expand using kind of an overloaded version of the subdag operator into all these other nodes. So rather than just having the tree result, you can actually dig into which conditions were met, or see all the other conditions that were met as well, or get some condition names. Yeah, and then basically with that C that was there, that becomes the input directly into the tree, which is a potential output once that the like conditions are met. Yeah, and then scorecards, they basically, as mentioned before, used for credit scoring mostly. So the idea with them is that you basically score a whole bunch of input variables and then you assign values to them. So in this case, we have two variables, numerical and categorical. And then variable one, you're trying to determine if it's in the range of 0 to 1, you'll assign it a value of 10. And variable two, you're kind of doing a exact match. So if it's categorical, is it exactly A, B, or C? And then you'll assign it a 10. And then at the end of the day, all of those are added together to calculate a final score. Decision tables are very similar, but you basically have, in this case, two variables. And then you're trying to work out if this variable one matches between 0 and 1, and variable 2 is between 0 and 1, you'll assign it a value of 1. So that's just basically like a lookup table to try and work out pricing based on like bucketed variables. And then those two components also fill out to a DAG in the Hamilton graph. So scorecards just create these two components. That PD is just the probability, like normalized score. And then the decision table has also a few values that you can look into. And we also include like some trace for some of them, so you can actually kind of dig into some of the results a bit more. So yeah, to dig into how we kind of achieve this, each of our Hamilton modules, we add this extra initialized module to the bottom of the Python file, and that basically just injects this this like entry point. So it's a overloaded version of the subdag operator over a new function that's injected into that module. And the reason we have to do this is because unlike normal Hamilton like nodes, this isn't actually a function, it's a variable in this module. So we have to have our own custom logic that's able to detect that that variable exists in that module and actually build the various nodes into that Hamilton graph and inject it in there. So that's kind of the entry point that we use. And then like each of our components inherit from this variable node. So we're able to see if it inherits from there. We can run this compile, and then the compile creates a, so yeah, with that compile, we're able to do some sort of like optimization. So for the tree, we can flatten it out and produce like a lookup table essentially. And then each of the different functions in that tree, we can have this like convenience decorator for, which is creates node. And then that will actually be injected as a node in the final Hamilton graph. The is namespace just means that that's like the final result of this component. And then internally, we also allow, so for instance, format inputs here can go to this conditions met, and that will automatically be orchestrated in that Hamilton graph. So each of these components, we also use Pydantic for the configuration. So because they're Pydantic, you can serialize and deserialize them. And for that, we kind of gone away from some of the traditional approaches in these rule engines. A lot of them use user interfaces, which are backed by configuration. And then they have code that runs this configuration to like execute those rules. But for us, we wanted our data scientists to quickly be able to get these out into production. So we have a focus on the code where the data scientists first develop everything as these Hamilton DAGs. And then we have subsets of components that we can extract as configuration. And then on top of that, we build very specific user interfaces that you're able to tweak certain values in. So the advantages with that is our data scientists have to do less upskilling because they don't have to learn a whole new user interface or a new specific language just to get these like decision layers deployed. It's also a faster time to value, like they can get these out really quickly because they already have their code in Python. So they don't have to do too much to wrap it in that Hamilton DAG or as this particular node in the graph and actually just get it deployed. And then we also get to exploit the Python ecosystem because it's already in Python. You get to use all the modules that are available to us. So yeah, here's just a kind of brief overview of our infrastructure. We deploy everything on SageMaker, which allows us to firstly expose the model as a endpoint. So our model is exposed using a Starlet API, which is basically the thing that runs Fast API. And then, you can request it with live data that we expose through an API gateway. But the benefit of SageMaker is that it's able to automatically orchestrate this model for batch processing. So you're able to say you want to do a batch process job with this model, and then it will read the data from S3, do micro batching, invoke the endpoint, and then actually store the results of those micro batches back onto S3, where we have internal jobs that pick it up and store it into our data warehousing solutions. And then we try to follow the similar standard to the sklearn containers. So they have this inference.py file, which you can override to determine how the input data is transformed from the raw request, how the model is loaded, and then how the response of the model or the result of the model is transformed again before it's returned back in the API. And then we also have a config manager class that you can override to load the config from any store that you need. So that config can be used then to build up those trees or the scorecards or the decisioning tables. And then, and then it's just your normal Hamilton code. We normally use the main Python as the main entry point, and you can put in all your other like subtags internally in the same folder. So yeah, that's pretty much our infrastructure. We obviously just have general CI/CD integration with GitHub. Okay, yeah, so now onto the demo. So I wanted to do like a mock fraud demo. That's very far from what we'd use in production, but I think it will give a good overview of our development process, how easy it is to get these flows like from inception into production, how quick it is, how useful it is to be able to use those overloads and the like sub-DAG parts of Hamilton to extract the information you need. And then finally, I just want to show how it integrates with the UI. So yeah, I think it might be just a good time to check if there's any questions before I go on to the demo.
Hi, it's very interesting so far, and it's nice to see how far you went, like from the basic Hamilton constructs. Let's say, I'm curious, which of the like core Hamilton feature do you use the most, or like that provides the most value?
Yeah, so I mean, just being able to use like sub-DAGs or like say which outputs you want and which inputs are already useful. But then, yeah, the sub-DAG operator probably on top of that is the next most used. Every now and again, we use like some of the other ones like parameterize or parallelize, you know, those explode and stuff. But yeah, I think sub-DAG is probably the most used for us. Yeah.
Cool. Thank you.
Okay, so here's just a notebook, just a disclaimer that it's a toy example. It's not a good example for any real production use case. But over here, normal development workflow would be to load some data, in this case, some mock transactional information, like how trustworthy the beneficiary is, some transaction amounts, and yeah, just a bunch of features that were made up. And then from there, you might want to do some sort of feature development. So trying to calculate the beneficiary's age or calculating some ratios. So with this, you can yeah, show the DAG and actually execute it in that notebook. And what's nice is this write to file gets it already ready for production. So every time you make a change here, we save it to that source directory so that it's yeah, up to date. And then you can start integrating more complex models. This might be some like cat boost model or gradient boost model to try and predict what are the chances of a particular transaction being a fraudulent transaction. In this case, with the hype on LLMs, I thought it would just be funny to directly ask a LLM agent if it thought the transaction was fraudulent or not. So I just format a whole bunch of transactional data, and I ask the LLM if it thinks it's fraudulent, and it must just reply with yes or no. So that was the more complex fraud detection model. Obviously, probably not a good idea for production. And then on top of that, you can start using some of the like extra components that we built. In this case, the tree component, which we have basically various rules that fire. So if the LLM thinks it's fraudulent, and then a few different like features that you might, like some of the experts might come up with to try and target very specific use cases. So that builds that DAG. And then you can also visualize the tree just to make sure you understand everything that goes on internally. And then, yeah, you can orchestrate everything together and execute it to see that it's working locally before you get it deployed. So yeah, in this case, it just brings back the decision, like should it alert or allow the transaction or should it block it? And then on top of that, you just need to create this inference.py file. For a lot of the models, it's like you don't even need it. But in this case, I wanted to log the executions to that Hamilton tracker and just have a few extra steps in that, in the way I build the driver. So I saved this all to the source directory. And then at that point, you could actually just commit it and deploy it in our platform. But yeah, for the demo, I'm just going to run it as a local endpoint. So yeah, it's just basically a fast endpoint. Usually not so slow, but I think it's okay. Yeah, there we go. And then over here, you can just make the request to it. So this is the JSON version of those transactional information you saw earlier. You can invoke the model. And then, yeah, the LLM takes a while. So, yeah, but in this case, you get the results. But where the power comes in is you can actually override stuff. So if you feel that, like maybe the LLM model isn't doing as you expected, and you just want to override all the results of that LLM model to false, you can just add that into the override section. And then you can invoke the model as well, and then this will return the results as if the LLM always returned false. And then finally, if you wanted to dig into like how particular rules performed rather than the whole flow as a whole, you could also say you're only interested in these outputs, and then just invoke that and you'll get the results of just those two like components in the DAG. Yeah, and then the whole thing was just strapped onto the Hamilton UI, which just provides another level of usability, another way that you can kind of look into it. So over here, you can see that first execution took 5 seconds because it had to call the LLM model, and then the other two models were a lot quicker because they didn't have to invoke the entire DAG. And then you can like drill into how long each of the execution steps took, or what code actually ran for each component of the DAG. So yeah, yeah, very useful stuff. Yeah, that's pretty much it. My side. There's a QR code for the decision engine if you want to see it, and then obviously I'm sure everyone here has a link to Hamilton. But yeah.
Thank you for your presentation. It was super informative.
Thanks, I appreciate it.
Yeah, that was great. Thank you.
Yeah. Yuan, you have a question?
Yeah, yes. Thanks a lot for presentation. Yeah, I'm really excited to see how it's deployed, because I'm also data scientist in the credit risk field, where we just started using Hamilton for credit risk modeling pipeline. So I have like 2 particular questions. One is about the feature engineering like part. And in the example, you show the example of a single application or person like inference. I'm just wondering, for the batch processing, how would you handle the feature engineering part? For example, say when we're working with transaction data, normally there will be a one-to-many correlation. Say one application profile have like maybe 100 of transactions. Then you will, when do the batch processing, we need to do some sort of group by function. So how would you handle that?
Yeah, so it's kind of like twofold. Our data scientists would probably deal with that beforehand, and they would build these models using the normal processes. So we use like Redshift there, and we have ways that they can query that raw data, do like the aggregations that they're interested in, and just kind of see what features are interesting to them or what is useful before building the models. And then when it gets into production, we would have something that actually invokes this model or orchestrates the calling of this model by first pre-computing some of those aggregations, or getting the records that are needed to invoke the model. And then over on this side, it would basically just be given as a single payload with all the required information. And then from there, it would kick off using like general pandas aggregations.
Gotcha.
Yeah.
Thank you.
To add to that, Yuan, we have some blog posts that sort of illustrate how to do this with feature engineering in Hamilton using pandas. So to how to say like, okay, this is how you do an aggregation in offline mode. This is how you do an aggregation in online mode, and here's how you switch between them.
Yep.
I can post something, because that sort of adds, I think, to what Sholto was saying.
Gotcha. Yeah, thank you. And my second question is that for the decision rule itself, I noticed that you have the decision rule within the code. Have you tried, like, say, have the decision rule as a separate JSON file or config file? Then you load it from outside, such that you can maybe like edit the decision rule in real time.
Oh, so basically adding a new rule to that decision tree. Is that what you?
Yeah.
Yeah, so for our scorecards and our decision tables, I didn't actually show the code for it, but you can load the whole thing as a config. So you can do that. Decision trees were a little bit more complicated. We haven't got it fully configurable yet, but the idea is that you would be able to actually load it from a JSON file, and you can you can basically do exactly that. So from the JSON, you can add a new rule. I want to try see if I can find a quick example. I'm just going to share screen again. Okay, yeah. So for instance, a decision table, rather than having the whole code to build the decision table, you can just say from config, and then you give it a key. And then when you build the Hamilton DAG, you just basically give that key into the config parameter for building it. And that can look something like this, where the entire thing is defined as config. So yeah, we have that for most of the components, just not the decision trees as of yet. But yeah, the idea is to get there.
Yeah, guys, yeah, thank you so much.
Yeah. Actually, question on that, Sholto, like would that, how would your change management process kind of function? We still have to have people kind of submit a pull request and other stuff to kind of change that config, or because my only worry is that with dynamism, it's a little hard to figure out what's going on without a lot of good observability. So.
Yeah, so it's basically not a one solution fits all. A lot of them we recommend just keeping the config as part of the code, because obviously then everything's managed together and you're sure it's working. But some places they want to be able to change certain values on the spot. So we're working kind of in a way to make sure that the config is only applicable for code above a version. So you would typically say for this config value, it only supports the Hamilton DAGs above this version, and then you can ensure that kind of the synchronization between the code and config. But you'll always keep that lineage of different versions, so you can roll back. Yeah.
Cool. Cool. Anyone have any more questions for Sholto? All right. Well, thanks, Sholto. Yeah, super excited to see the amount of stuff you built on top of Hamilton. That's awesome.
I appreciate it. Thank you.
All right. So, all right. Cool. So, so the next part of this, probably going to try to take maybe 20-ish minutes to kind of go through a few things, and that is some recent features, kind of improvements. So first off, big thank you to Charles, Jerne, and Thierry. Elijah and I didn't contribute much to this, and so in which case this came from open source contributors. So thanks very much. The first two I'm going to walk through are just going to be kind of code examples, and then for mutate and pipe output and caching, I'm actually just going to walk through a notebook. If you have questions, yeah, feel free to jump in and ask. But otherwise, we did release a few more things, but these are just some of the things I cherry picked so that we could kind of get through in time. So the first up is so if those who don't know, so Hamilton does have a lightweight data quality kind of mechanism, and so you can annotate a function with check output, and so Hamilton ships with with pandas kind of support pretty easily, but there are ways that you kind of expand and kind of extend it. And so thanks to Charles, he added the ability to actually specify a pydantic model as something you can validate against. And so there's two modes of using it, right? So the first is you can kind of pass in a model keyword argument to check output. This has to be a pydantic model, and then given some sort of dictionary, right, you can then use pydantic to validate the output of it. And so if you're doing more web requesty stuff, right, then this is where potentially this could be a fit. The other mode to kind of use it is you actually annotate the type with it, and you use under the hood. This is using the same code path, but we just kind of expose two different things to make it a little more explicit. And so these two functions are equivalent. And so really this is a bit of a question to you as to how you want to use it. But suffice to say, you can now use the Pydantic's capabilities to validate outputs of Hamilton functions. Any questions?
I think they're slightly different. The like subtlety is that the one above, it's the thing you return is not a Pydantic model, but you can ensure that you apply the same validation. So this is useful if you don't have Pydantic everywhere in your code, but you want to ensure the right shape. And the bottom one is, since you create the Pydantic model, you're just checking the type.
I'm pretty sure they actually both work with the dict thing.
Okay.
But I think this is the more ergonomic way of putting it. The Pydantic, the check output will like to do whatever Pydantic can consume, which is either a dict or a Pydantic model. But I think that you're right, and this is how I would use it. If you want to just put it on, but you don't want to change the output type, then this is a nice way to do it.
So in a sense, it allows you to have the Pydantic validation, which is very rich, but not necessarily change the functions to be using Pydantic. That's the beauty of it.
A second thing we kind of added was a static validator lifecycle component. So one of the context for this particular request was you can tag functions in Hamilton with various types of metadata. How do you ensure and validate that everyone has used things kind of appropriate, right? And so I'm showing one function here. So before running, so there is a run to validate graph kind of function. So basically, given a Hamilton graph, you can kind of validate it all at once, or on a per kind of node basis or Hamilton function. You can easily write now a function that then can say introspect things about it. And so, in which case, this is an example of a tag validator that's just making sure that, like, hey, if you have a table name, you got to make sure that it's not empty and meets some sort of standards, etc. But this is one way that you can, in your CI pipeline, have something that runs that then validates to ensure, or before Hamilton code runs, even to validate to ensure that things are as expected. And so excited to see people use more of Hamilton's metadata and graph structure capabilities, and then building things like this to kind of validate it. So as an example, you would just kind of instantiate this tag validator and add it as an adapter. If there were issues, this call would fail, so you could wrap this in a try except. If it passes, then there's no exception thrown. Questions? Yeah. All right. Oh, cool. So two features that I'm excited for is mutate and pipe output. So I am going to jump over quickly to a notebook here. So the motivation for this is with Hamilton. I think this is cool. So the motivation for at mutate is that you can rather with Hamilton, if you want to say you have features and then you want to apply some sort of transform to it. So I would have to then write a new function like transformed features, right? That takes some features, right? And so this is good from the perspective that Hamilton gets you to do things that are verbose, right? It's very clear, it's very understandable how data changed. But this can potentially, if you're trying to do a lot of things, but downstream users don't really care. That you don't have to rewire your downstream consumers each time you kind of update a transform or something like that. This is where something like at mutate could be beneficial for you. The way that it works here is like if you have some function that outputs some sort of data type, doesn't have to be a data frame, you can apply what we call a mutation to it, which will basically, if I kind of run this code, right, will allow you to have this function to be named whatever you want it, but basically in order, it will apply normalized columns, right, onto the output of features. So this is an easy way then to without having to change this function at all, I can inject and kind of input different kind of mutations. And so a common potential use case for this is like if you have to normalize or a data set or remove outliers, right? And you want to do this across the board. You don't want to have to necessarily write these new functions. Instead, you can use the @mutate decorator, specify a function pointer. So one of the constraints we recommend right now, or the constraints, is that these mutate functions have to happen. Okay, so Anthony, we can. I'll just finish here, and I can let you ask the question to Sholto. You can, basically it has to be within the same module, because we want you to kind of curate code to be in the same place. We do, if this is an issue for you, say you want to mutate things outside of a module. I don't recall whether we explicitly enabled it. Elijah, you might have to remind me. But otherwise, this is, I want to say, a cool feature too. Yeah,
I think it's currently disabled, but that's something we're waiting for input on. The reason, there's a specific reason it's disabled, which is the Jupyter Notebook case, which is a problem solving where it keeps state and then it does some weird stuff. But otherwise, it can totally work.
Yeah. So you can, So like the theory. The other features, so you can pass in kind of values, but you can also pass in, the source parameter and kind of have it depend on. So if I rerun this again, right, we can see here that we have some input now. Depends on is required as input to kind of run this, and the way that it's wired is it's wired into the kind of the value food. So this then means, like, say, if you're iterating, right, if you just want to turn something on or off, right, it's just a matter of kind of commenting things out. The other point to note is that if we change the order of these two functions, these two kind of mutations, right, the way that this works, it works tops down. So the way that then you'd read it is, right, so any mutations are applied in order of how they're specified in the file. So if we do that, we kind of see here that outliers is now first before normalized columns.
Yeah, I think Stefan will add details to that after, but you see from the visualization that behind the scene it uses the pipe construct. If you're familiar, if you can just scroll a bit, Stefan.
Yeah, I mean, so I was gonna go to sorry.
Like
you
have the width that's added to the name. So like you have features dot with remove outliers, and remove outliers is the name of your function. So that's how you can tie the two together.
Yep. Now this is using makes use of another new decorator, which is a little more explicit. So instead of a mutate, we now have also a pipe output decorator. So what this does is, on the output of a function, you can pipe various transforms to it. So these two pieces of code are kind of equivalent here. This is, again, you can comment this out, but this is if you want to say be a little more explicit as to what transforms and what are applied when, you can use the pipe output function as a decorator. We had a prior decorator called pipe. We have now that's still around, but we just renamed it to pipe input to help delineate the two of when these pipes are kind of applied. But these are, I'm excited for these two new things that basically enable you to not have to rename features if you want to apply some transforms. And so you have two approaches to it: is you can add pipe output and then or use mutate and get the same result. Okay, question you want?
Quick question. I noticed that there are some new nodes created here. Are those new nodes also accessible?
Yeah, so this is part of what the graph algebra does with this. The same thing, pipe output and mutate do it. So it creates all of these, and then features is the final node. They're all accessible. We may consider renaming them depending. So I wouldn't say this is a first-class part of the API, but I think it's safe enough to start using them and mess around with them if you want. They're really mostly around there for debugging.
Yeah, and so you could technically, if you do features dot with normalized columns and you request that as an output, get that as part of the output of.
And then for debugging. And then if you like, yeah, right, in the UI, you'll see that, and you'll see summaries for that show up. So,
yep, cool. All right. Any more questions on this stuff? Else, I'll.
Yeah, there was a queue, so I'll give the speaking turn to Jörnej. If you maybe you have an answer, and then Sholto has his hands raised.
Yeah, Jörnej, do you have something to add? Else, I know Sholto and Anthony actually had a question, so definitely wanted to facilitate that. Okay.
You want to? You can type it, if you want, and then we can.
Yep. Otherwise, I guess Anthony and Sholto, did you guys want to answer the question?
Yeah, I mean, happy to. I kind of answered in the chat, but basically we do have other. Let me just read out the question. But my understanding is basically you just wanted to find out if we use any other enterprise decision engines, and how's the transition from that to Hamilton. And basically we still do have other ones. That's not always like easy to shift everyone over, but the power of like using Hamilton is we can integrate to a lot of the existing solutions with API calls, so they can continue using those solutions. And then we'll have a node in ours using potentially like the async as well that can just invoke out to there, call that existing solution, and then return the result. And then slowly, as we see the need, or we see that it's a good candidate to move over, we can integrate it. But yeah, there's some departments obviously internally that we still need to win over some trust with. And yeah, just kind of like show them that it's a better way, because like people in doing their own kind of in their own ways of doing things, essentially. Yeah.
Right. Okay. So yeah, so Jörnej, you just had yeah. So oh, go ahead.
So Jörnej was pointing out that the last node there, the with remove outliers, is just the same as features. We just do this namespacing thing where first we namespace it for the internal one, and then for the external one, which is features, we just have an identity function. A little bit about, again, these internal nodes, I think, are more for debugging than for making it something that relies on in production. So we reserve the right to change a little bit about how this works, but that final node that features exist there is absolutely something you can rely on.
There are ways that you could potentially depend on the inside of this stuff. The only way to do that is like with the inject thing. But as kind of Elijah mentioned, we might change a little bit of how this is structured internally.
Yeah, but to clarify, I think the names are they might change, but they need to be reliable, because pipe input is slightly different.
Yeah.
In pipe input, features with remove outliers would be the last node, and features would be at the beginning.
Yep. Yeah, exactly. And that's the contract with this, right? You get it'll create a series of nodes. Pipe input will put the last node at the reliant node at the beginning, and then pipe that all the way and keep the name of the node that's the function. Pipe output will do the same thing on the other side. So it'll change the name of the function, make it so it depends on the right things, and then the node that you actually get that is the result of that function is the last one. In most cases, you probably won't care. You'll just be running these transforms and looking it in. But when you get to that sort of 20% case, you look at it for debugging it. Is helpful to know that.
All right. Sholto, you had a question?
Yeah, I just wanted to check. Obviously, you inject that features raw. So if you have like a function there called features raw, then it would be a conflict, right?
Yeah, so that's what Thierry was actually just pinging me about this, and I think that we should change this to features.raw.
Raw, yes,
which is probably a cleaner way to do it. Yeah, we should. I think that's a good point. That and that's a conflict that you actually could hit, right? You could easily see having a features raw and then a features, then being very confused about why it doesn't work. I think that's a change we'll make, and again, that's kind of why I was saying that we reserve the right to make a change, right?
Yes.
But yes, to be clear, features raw is an internal node here, and we're opening a GitHub ticket on the question.
Awesome. All right. So with that, I was going to move to caching. So
Yeah, maybe one last thing. Pipe, I think, is appreciated for working with data frames, but I had a lot of success using it with LLM workflows, because you might want to do like text, extract things from HTML and then parse it and then chunk it into paragraphs and then chunk it into sentences and do embedding. And then the pipe construct allows you to toggle steps also and reorder steps very easily. So that's something I suggest looking into if you're working with LLMs currently.
Cool. Oh, cool. Super excited for caching. One of the things that we kind of done is enabled you in kind of one line, just in the builder to kind of, with some batteries included, get some pretty powerful caching constructs with Hamilton. This notebook is available under examples caching tutorial notebook. So if you really want to kind of go through this yourself at a slower pace, this is what I recommend. So I'm just going to briefly walk through just the high-level constructs or concepts, just the things to take away here. With data work, and so we're initially focused on caching here being something that you want to use in development. This does have extensions to production, and so do come chat with us if you're interested about that. But the idea is, okay, with a lot of data ML work, or things that you're doing with Hamilton, it's generally involving data. Ideally, you don't have to recompute things if things haven't changed. And so that is the kind of the core premise that we're trying to enable here. And so one of the ideas is, like, say we have a simple graph here. It takes in some raw data. You can imagine this being, simulating something, pulling from a file, database, or external service, right? And then we're processing. When this runs, say we're iterating or developing, right? We want to, if it's new and hasn't been run, we should run it. And so I have some extra logging here that's going to tell us a little bit of, like, what's going to happen. And so I have two doubled up here because I instantiated the logger twice. So we're going to see a little bit of double up of logging. But the idea is that, if we were to rerun this code, right, we shouldn't have to recompute things if code or data kind of hasn't changed. And so if I rerun this example again, we can kind of see that we didn't recompute anything, and so one of the things we added is that you can access a cache object on the driver and then kind of see the results of the prior run, and we can kind of see here that like we didn't actually run those functions, we just pulled data from cache. There's a few things around kind of cache keys and kind of how we do it. I'm not going to necessarily dive towards it, just to mainly just give you a bit of a mental model. Since in your development workflow, right, you're likely going to be going back to here, adding some new function, right? So in this notebook, we've done this serially, and so that's kind of just what I'm going to show. But say you wanted to add on, a different processing step, right? Amount per country. The idea is that, well, Hamilton is smart enough, given the way that functions are named and function input arguments and the code inside, we can actually know whether we have a pre-computed value for this or not. And so you can see here we've added a new node. We just kind of adding the caching construct, right? And then you can see we're then kind of running and requesting amount per country. Now, since I ran this previously with the kind of same input values, you can kind of see here that we actually got there are results in the cache. And so you can see here we didn't recompute everything from scratch. Instead, we only recomputed the thing that was new. And so this is part of the idea, is that as you're developing, as you're iterating, like, you don't need to recompute stuff. We can just pick up from where you left off. And the cool stuff that we're kind of doing under the hood is that, like, hey, if inputs change in this graph, so like say we change the cutoff date, well, we should ideally recompute only the paths in the Hamilton DAG that are impacted by this kind of change, right? And so you can kind of see here that raw data didn't change, but then we recomputed this branch because we changed the cutoff date, and we recomputed not only process data but amount per country. questions thus far? I'm following. Yeah, Adam, go ahead.
Do you process the cache actually between instances? So when I start my notebook, I can still basically reuse the cache?
Yeah, so at the top here, I kind of glazed, I didn't talk about it, but right now, the default batteries included is that this goes into a .hamilton cache directory of wherever you're running kind of instantiating the notebook. So locally, so if you want to clear your cache, you can just remove this. But the default kind of, there's like two things, a result store and a metadata store. They're both just running off your local file system. Yeah.
Okay,
I'll
perfect. So
go ahead. Adam.
in answer my second question, so you're not using something like DAGDB and underneath, so you store it as a files, so it could be reused as well. Okay. Yep.
We have extensions there. So like you see that this is a data frame. So the default is we pickle stuff. But we do have the ability that you can tag and provide, you know, a format. So say you want to save this to Parquet. So there is there's as you can imagine, we're trying to include the batteries included, but then with the hooks that if you need to customize or change or then do that.
Perfect, makes sense. Thank you.
Yeah. Okay, there were some ends that went down, but if you want to ask questions, feel free. I just wanted to add to Adam's question. By default, we store things on disk. This is nice for notebooks because if you shut down your notebook or you restart the kernel, the next time you execute your DAG, you will be able to read values from cache. But we had requests to also provide an in-memory cache. So that would be a middle ground where you have cache for the lifetime of the notebook, but when you close a notebook, like you lose your results. That would be an option to enable in the future.
And to be clear, Yuan, it works. It is not just in a notebook. It works outside of a notebook. I think to add points to what you guys are talking about, we have plans to also make it so it's not file system based necessarily, so that we could have, say, an S3 based cache, which means you could run it in, like you could start an Airflow job with your Hamilton thing, then it dies and you get halfway through and then you launch again and it can pick up from where it left off because of the cache. This is a pretty straightforward thing to do. We're just sort of working with a few different use cases to make that happen. So that's
one cool pattern is that you run a script or you have something on schedule, it fails, then you can open up the results from cache in your notebook, for example. And we're looking to improve that workflow, but that allows you to resume exactly where it failed and inspect the results. So Sholto, if you want to tell us your question.
Yeah, I just wanted to find out if we can actually exclude certain nodes from being cached.
Yeah. So in the notebook, we'll kind of see there's a few ways that you can ignore stuff, but you can either obviously annotate a function, but then there's also when you're kind of instantiating this cache, there are some options that you can also pass in to say, hey, don't cache these things or do. And so if we don't have the customization, then do open a ticket, but we feel we at least have starts to try to help you.
Yeah, it's a very complex feature, so we try to provide a long tutorial, but if there are patterns that you feel are not covered, like we're very eager to learn about your use case, so feel free to ping us.
Yeah. And so
Justin posted, this is a fun one, on the thread for caching, noting asking whether or not we're using Merkle trees, and we are. It basically is a Merkle tree algorithm because we're cascading hashes from, like, a Merkle tree is cascading hashes, kind of like Git. So it is. But that said, I think it's more configurable than that because we have all these different sort of ways that you can cache your data, and we're still working on making it easy to configure. But there's also different possibilities there.
So and so one of the things that so if inputs change, right? So you should rerun things, but also say, hey, I'm changing data, right? And so one of the things that that happens here is that we can change some we have an existing DAG. I came back, and I want to change some internal value, right? We can Hamilton will know that, like, oh look, hey, process data changed, the outputs changed, and we also need to run output amount per country, right? And so really trying to make it easy so that if you changing or updating code, right, then again, just like inputs, the only paths that are walked in the graph are the ones that are needed to change. And so under the hood, basically, you can think of it as like, yeah, we're trying to hash the internal parts of the function, hash kind of the inputs. We're trying to get kind of data hashes as well. And so there is some caveats around, we need things that are hashable. And so what do you do if you don't have a hashable type, etc. But like there is, we have some paths and some things we're working on to ensure that we cover everything. So Adam?
Sorry, I might have missed it from the code, but one of the scenarios that we have is actually that we run simulation based on different configuration. Can I use a cache for it and store in different versions based on simulation and then run comparison?
So idea is if they're running the same code and imagine they had the same inputs, then they should technically only have to compute it once and reuse that value from cache. If I got your question correct. So can the different simulations share the cache is kind of how I understood it. Was that your question, Adam? Or
generate different caches based on parameter changes and then have ability to compare between basically those versions. So I might be abusing the current feature idea, caching idea.
I want to say you could configure different caches for each of those different runs. This is what I guess maybe the Hamilton UI is something that we could extend and then like, so the Hamilton UI currently doesn't plug into what's saved on cache, but there's something that like caching and observability are very, very much tied together. So in which case we'd love to, I guess, maybe a little bit more about what your requirement there is and from the comparison perspective. But for each of those runs, you could configure a different cache.
Yeah. So initial ideas for development, but yeah, I will run it by Sholto and we will see how the detailed requirements are, in particular for production. That's cool. Very, very good feature. Thank you.
Sholto, you had a question?
Yeah, sorry. Yeah, lots of questions. The caching, do you just cache the raw thing? So if you change that doc string, will it override the cache, or do you cache the abstract syntax tree?
So to be exact, we get the source code via inspec, and then we parse the source code to remove comments and doc strings. So the source code actually like implicitly hashes the function name, the function signature, the return types, but we do ignore doc strings and comments.
Oh, that's cool. Thanks.
I mean, if that's not the case, file a bug. Cool. Let's see. Right, and so there's one caveat, right? So say this raw data, like the actual underlying data changed here, right? We wouldn't know that by default, right? And so if this function went to a database, did some select statement, right? We wouldn't necessarily know off the top, like without running it to know where things have changed. And so this example here is just showing that, oh, look, we nothing changed, right? But like there is, where is it? Changing. There are kind of ways around it, right? And so there is ways that you can kind of specify, hey, like always rerun this function. Don't do it. I mean, Thierry, I guess if I'm butchering this.
No, but just before, like, essentially what we try to do, like with Hamilton, if you're familiar, there's two levels. Like there's the data flow level. This is the cell we're looking at. You can use decorators like load from, save to, but there's also the driver level. This is where you build your graph. This is where you execute your graph, and you have a lot of isomorphism or like similarities. So you can use materializers with the from and to load and save files. We try to do the same with caching. So you can specify things on your node with the @cache decorator, but also the driver level with the with cache clause. So here we say always recompute raw data. But you could also decorate your raw data function and say always recompute. These two should be equivalent, but we always make the driver level have precedence and override the cache. decorator because it's closer to execution. So you could have like in your notebook, you want to have the caching, like the full caching experience. But in production, you want to make sure that raw data as the behavior recompute, you can use with cache and say recompute.
Yep. But otherwise, in terms of like to know whether you should recompute something, right? This actually, the interesting thing is that you might actually want to break this, if this was doing a SQL query or something, break this up into two, where you have one query that is, trying to see whether any data has changed and use that as a bit of like a hash to know whether to kind of to skip stuff or not. But this is where, we're looking for feedback here. Is like, is there a better way or a better behavior to kind of, intelligently figure out when to run a SQL statement or not, right? And so this is where, just to kind of plant some ideas, is that right now it's like you need to kind of hand tune and specify, but then there could be other patterns where, if you could somehow provide a data hash, right, that could be passed in as input, we can then maybe intelligently know, then, okay, skip raw data if we, if one of the inputs is the data hash or some constant, like we can kind of use that to figure out whether to run something or not. I'm not sure whether that explanation made sense, but if you're following, right, this is probably the only thing that you need to kind of think about more actively with the caching is like, if you're going to some place external, how do you know whether you should go to it or not? And so there are ways that we can, smarter or more intelligent ways that we could be approaching this.
And if you have any feedback on the APIs and anything, obviously we're going to keep this backwards compatible, but we can add new things to it. We've got sort of this nice 2-layer design where the top layer is sort of meant to be an easy API, and then we've got a bunch of lower level stuff that you can use, which gives us some flexibility in building out more features to make it easier to use. So would love feedback. Please reach out if you have anything. We'll be able to respond to it. This is a feature we care deeply about and really want to invest in.
Yeah, and then so just to, as I said, this is a very quick overview, and so just to the last one, just to we pickle things by default, right? And so pickling does have certain caveats, and making sure you have the right Python dependencies to be able to reread it. But we do have a pluggable system where you can kind of plug into the serialization feature, and so the kind of way to kind of do that is that we have a @cache decorator. So it's not a tag, sorry. Under the hood, it actually is using kind of tags, but the idea is that you can specify a particular format for this, right? And so this then can be Python version independent, right? And if you had some custom serialization or custom object, this is we have hooks that make this kind of pluggable. And then and then lastly, we're trying to make sure that there's never a question of like, oh crap, what happened? What did it do? Right? The .cache object after something is run has a bunch of introspection and methods, so you can always at least figure out. So this is where we haven't added the connection with the Hamilton tracker quite as well, so to speak, but this is something that we expect to also have in the Hamilton tracker, so that if you're using the cache and the tracker, we can also then help you more easily debug and introspect and understand what was used in the cache or what wasn't. But just and so it's easy to kind of given a run, figure out whether it used something, and then we kind of store the logs. But otherwise, let's see, let's run these two things, see if that happened. But otherwise, I don't think there's anything too relevant to kind of talk about. But
yeah, again, it's a very long notebook. I think it's valuable to go through it once when you start digging, or especially if you find a bug, maybe go through the notebook. And we put a lot of effort into the documentation too, because the challenging thing with caching is that we cannot cover every scenarios by default, but we probably have some options or some path for you to solve your problems.
And then just to give you a little bit of sense under the hood is like, in terms of extensibility, right, this is where we do have kind of different stores or different places that you can store this metadata. We're trying to make that pluggable. And so we ship with 2 out of the box, but this is where, depending on your production use case and other stuff, like this is where you can start to plug in your own custom versions or collaborate with us and we can work on something. So with that, I want to say, yeah, thanks. If there's anything that anyone wants to kind of talk about, we can. But otherwise, just to advertise, the next one meetup will be in December. If you have something cool or you want to demonstrate what you've done with Hamilton, we'd love to highlight you just like we did with Sholto. But otherwise, if no one has anything to kind of, so rather, I'll give 30 seconds for anyone to kind of, I don't know, request or talk about features or things that, you know, because you have, you know, our collective attention, let us know, or just unmute yourself and say something.
Right before that, I just want to say Thierry put in a huge amount of effort into caching, and there were like 10,000 edge cases, a bunch of things. Hamilton is a pretty complicated library right now, and we have a bunch of different ways of doing it. And at some point, we'll consolidate all that, but that made caching harder. And Thierry really just like ran right into it, came up with a whole design, turned it into something that's like kind of a platform as they're having this sort of side channel conversation on the announcement thread. So I want to say really good job there, man.
Yep. Yeah.
Very, very appreciative. I think this like is like, I keep saying this as table stakes feature that we should have released with the original Hamilton, but it's so hard to get right that it took us like a year or two to actually figure it out. And I think we actually got it right. And we have just the right extendable constructs to really build caching system that's good. And if you look at compare it to other caching systems that have been released, because it's kind of hot these days, you'll find it's just far more sophisticated.
Yeah.
So super excited about that. I think we've got a really, really good platform here, and I'm very proud of it. So nice work, Joe.
Yeah. One note is like async. So Hamilton does have async support. So we are, so with caching and the mutate decorators and the pipe output, we just need adding async support there is on the roadmap. So if you're using async, do reach out. But otherwise, yeah, to echo what Elijah said, this is pretty big, and Thierry put in a lot of effort. And so super excited for you guys to try it out, and obviously hopefully not find too many bugs. And if so, yeah, just let us know and we can work on them. So.
Yeah, I just wanted to say congrats. I thought this was really cool. I was chatting along, but I didn't want to be an audio distraction. But thanks for that, and then thanks for adding the Jupiter cell magic. That worked like a charm, and I've got that working in some code. And I guess like the only other thing would just be the I feel like there's I'm putting together the pipeline piece by piece using those Jupiter cells, and I'm realizing those can be serialized, and so I almost kind of want I want a simple, even simpler API, just to kind of like create a module and write things to disk, you know, in a source directory, kind of auto package something. So I'm just gonna I'll see what I can contribute, and but it's building up it's basically, you know, can I build the whole thing from a notebook and then check the output and then ship it when it's good. It's awesome work, so thank you so much.
That's a really cool idea, and I think that also gets to what Sholto is doing in his, where he had like a sort of nice, like well-organized set of files that if you did it all in the right way, you could then like stick it all the way to SageMaker. So something where it's a little more like opinionated, a little more structured, and gives you that all packaged together where you don't actually have to leave your notebook. Like that's super cool. I'm really stoked on that. The next thing we need is a way so it can pause like inline in a function and give you the same Jupyter autocomplete. I guess iPad stuff. That's
Yeah, I mean,
standard.
Yeah. I'll try to talk to my current client and see if they're okay with me just sharing like the sketch of the framework and the pipeline rather that I'm building. And it'll give you more of a sense of like just how this goes all the way down into features, you know, and then what kind of phases and where you want to have different kinds of caching. I don't know. But it's helping me like move the ball down the field. So thank you very much.
Cool. Thanks, Justin.
All right. Cheers, fellas.
All right. Well, yeah, if no one has anything, appreciate it again. See you all in December, and then if you want to speak, more than welcome to just hit me up.
All righty.
Thanks, everyone.
Thanks, everyone.
Thanks.
Thank you. Cheers.